Guys, in this video I'm gonna show how to find the deflections of a shaft using ANSYS. Okay, so in a shaft design, you always start first with um, doing equilibrium study to find forces acting on different parts of the shaft and forces acting on the bearing. And the next step would be finding stresses, and then you find the stresses at most critical point of the shaft, and then you find the required diameter at that point to meet your design criteria, your requirements. And after you have that diameter at critical section, all other um, diameters you decide, you can decide on other diameters based on the layout of your components and your shaft. As I said in class layouts, you typically, most shafts you see, they have the thickest part at the center is the thickest, and then getting closer to the bearings is going to get thinner. So the example from Shigley's book, we went through and we found with diameters based on the shaft, based on, I'm sorry, stress analysis. So here is the results. I summarize the results here and I show you the diameter, different points of the shaft. So you see um, the length of the shaft from the center of the bearing to the other bearing on the left and right is 10 inches. So you see, in this drawing, the datum is the left end of the shaft, but for our stress analysis actually and for our mechanical analysis, we just consider um, distance from bearing to bearing. The other, out of the bearing on left and right, they are not under load, so um, we just extend that a little bit, and assuming that we are gonna put like a retaining ring here on the shaft. So we have just room for that. You see on the other side we have room for retaining ring there, but that part of shaft is not going to be critical because there is no load acting there. Okay, so the datum, as I said, starts from the left. The bearing, the center point, center plane of the bearing 1 is 0.75, and then after that you have um, the diameter, by the way, at that point, at that section for the bearing, we considered at 1 inch. And after that, we have a shoulder here. You see, we need to consider room for, for the bearing, after the center point. So the bearings, this problem, we have not selected bearings, but in a real life problem, you select the bearings before actually this. So select the bearings and select the gears. So we are just here considering that we need that much room, like 0.5 inch room for, we are assuming that the width of the width of the bearing is like 1 inch, right? So when we go to catalogs, we can actually look at that and find the one that has 1 inch. And you see on the left there is room actually to extend the shaft if you don't find something exact like 1 inch. So that's not a big deal. Okay, so the shoulder for bearing shoulder starts at 1.25 inches, and the diameter on there D2 we found, we decided to have 1.4 inch, and after that we have another shoulder, and here we are gonna put the retaining ring. And so the groove diameter of the retaining ring is gonna be your diameter here, but D3, which is the diameter at our gear and is actually on the other side of the retaining ring as well. We found that to be 1.625. And alright, so you see gear 3, you know that the diameter was 12. We use that for to find our forces, and to force analysis. For force analysis you are going to need that to find your torques and um, your moments. Yeah, okay. And then at the center of the shaft D4 we decided to have 2 inches, and the shaft was symmetric on the other side. The loads on the gear on the right was larger, so that's why the gear you see on the right side has a larger width. So for that we have a 2-inch width as a teeth width, and then that gear starts at length distance of 7.5. The midsection of it is at 8.5, and after that we have we have a shoulder for retaining ring. Retaining ring is gonna put that gear in position. So the thickness we have considered for that retaining ring, as you see, is like 0.27, I'm sorry, 0.25 inch. So we have to find a retaining ring that is like it's gonna fit there, the thickness. Okay. And after that we consider the shoulder there. D6 again is similar to what we had for D2. We wanted to have symmetric shaft, and on the other side, and then we have the last shoulder for our bearing, and diameter D7 is 1 inch again. Okay, so in general it's better to have a symmetric design, because as I said, it's gonna make the job for the machine is easier. Okay, so alright, so now we have these diameters, and if you remember, we changed the material from 1020 cold round to 1050. As far as I remember, it was 1040 or 1050. I'm sorry, I forgot. Let me double check that. Yeah, but no matter which one we use, actually, modulus of elasticity is the same, so it's not really, it doesn't really matter. But just for the record, let me double check that. I forgot we changed it to. This is about the keys. Yeah, alright. So, and yeah, okay. So where we changed it, it was page before this. Okay. So yeah, so 1050. I'm sorry. So yeah, we had 1020 at the beginning, but we changed it to 1050 because we didn't have enough endurance limit. So, but as I said, it doesn't matter. Different types of steel. What is different is actually their hardness and their strength. Modulus of elasticity doesn't change. With For steel is the same. It's more modulus of elasticity depends more on the constituent material. Constituent, I mean, what I mean by that, I mean the composition, chemical composition of the material. But and melting temperature is like that too. So there are some properties of material like density, for example, also they don't change much. So but the strength and hardness are gonna change, right? All right. So now I'm gonna model this using ANSYS, and then at the end we are gonna compare it with hand calculation. Okay, so what I would like to say here, and I said that in class 2, in FEA analysis we usually try to eliminate features that are not gonna affect our results much. so to make the modeling easier. And in hand calculation, same thing happens. We make simplifying assumptions. For example, guys, somebody can model this shaft, all the features, and all you see those are slots for keyway. For example, keyway here. They're gonna definitely affect our the stiffness of the shaft and deflections, but um, the effect is not that significant. So, or you see this keyway. I'm sorry, the retaining ring, the groove for that, it's gonna affect this the shaft deflection too a little bit, but we are not gonna consider that effect either. Or other things that we are gonna ignore. For example, you see these bearings, these gears that is sitting on the shaft, right? It's kind of you're making. It's not like welded. The gear is not welded to the shaft, but it's kind of attached to it, so it's gonna affect the deflection too because it's adding more material, right? So I mean, but we are ignoring all these effects. All right, so let's see what happens. So you guys keep in mind these lengths, and I'm gonna put it on the side and start modeling this. But okay, ANSYS has another software, another code. Its name is ANSYS APDL. So I'm gonna use that. It may be new to some of you guys, but for shaft analysis, I think that is easier to use. So you see here mechanical APDL or APDL. I can open it and I'm gonna show you how we can model this shaft. And other thing I wanted to say, I'm gonna just model this like a line, a beam element like a line. So it's just a 2D element, very easy to do, and you will see that at the end the results are gonna be very close to hand calculation, and so it's an acceptable approach. Okay, so Apidol, let me give a little bit overview here. uh, so it's like a older version of ANSYS, and still is actually for more advanced applications. You have to use this Apidol. Workbench is more user-friendly version of ANSYS, and this is the direction they are going, but it doesn't have advanced capabilities as what Apidol does. So that's why they still keep when they release ANSYS, they release both Workbench and this Workbench for preliminary analysis, and for easier cases maybe um, it's it's like more straightforward, more user friendly, but this one will give you more features, more advanced features. uh, for example, you can specify here materials that are completely like non-linear, and input it here in all different directions. It has like different properties, so and so it's more advanced. But the application we have here, the beam element and the shaft, you're gonna see that modeling that inside Apidol is not really hard. It's very straightforward and easy. So I hope this recording will help you guys to learn that. Alright, so you guys know that every FEA analysis, there are three different steps, right? Preprocessor, solving, and post-processing. So with pre-processing, you guys know that you define your geometry, determine your element type, and meshing. All these are concept pre-processing, and then you solve it using here this option, and then you will have post-processing to see the results. Okay, so first step here, you can go into element type, and we have to define our element type for our model. So you say add. You see it, you have much more option here, compared to Workbench. I say I want beam element, and he says, he's asking, do you want like 3D element or 2D beam element, or 2D element with 3 nodes? It will have a mid node. I say I just 2 node element is adequate for me, so for my purpose. So I say apply and okay that. Okay, oh, I'm sorry, I added 2. We don't need 2. So, and then, so element type is um, beam 188. Alright, so that was again 2 node 1. Now I close it. Next, you have to specify the material. Alright, and our material, to specify material, I clicked on material properties and material models, and I'm gonna specify structural properties, and I'm gonna stay in linear elastic region, right? And my material is gonna be isotropic. It means that it's gonna have same properties in all direction. Modulus of elasticity. One thing you guys you need to keep in mind is that APDL is unitless, so you have to keep track of your units yourself. Make sense? So if you have like your modulus of elasticity in KSI, right? KSI, then you have to make sure that your forces are going to be defined in kilopound. And if your dimensions keep your dimensions in inches, then at the end, stresses you're going to have are going to be in KSI, and the deflections you're going to have in inches. Make sense? So it's up to you. So it's not like APDL, you have unit system. So you have to keep track of your units. So you guys know that for steel, you have 30,000. There is 10% uncertainty there, but we don't consider that here. So 30,000 KSI, and then modulus of elasticity of steel is 0.3. We can consider that. So I say okay. So keep in mind that our everything we have is like in KSI and inches. Okay, so Poisson ratio, PRXY is Poisson ratio, that has unitless, so we are good on that. So I close it. Material was defined. Okay, then for beam element, you see here for different type of elements, you may need to define different properties, right? So a beam element, my beams, you guys see that my element, my shaft, look at my shaft. I'm trying to model the shaft. The shaft is made of like solid pieces, solid circular pieces, right? So so I'm gonna have circular section here. So let me go here. Where was it? Okay, so here, and I'm actually circular section is like a common case, right? So you click here, common sections, and then ANSYS here has preset. As a preset is a different cross-section areas as preset here. So right now you see the effect. The active one is the rectangular one. I'm sorry, rectangular one. So but I want like circular, right? You see different types, common cases, like hollow, circular, because that's actually for shaft is also common, I-beam or other types, right? So for our case, our shaft is solid, so um, ID, it's gonna be the identification number for that section. So starting from left, I'm gonna name my, let me close this guy. So from left, I'm gonna try name uh, my sections, or my cross section areas by the number how I numbered the diameter. So this will be like section 1, D1, D2, D3, D4, D5, D6, and D7. All right. So let's see. So okie dokie. So okay, section 1, the radius is what? Section 1, the diameter is 1 inch. So the radius is gonna be 0.5, right? So I say apply. So that was defined. If you wanna like preview the properties, you can say preview, and it's gonna tell you ANSYS what is the area of that, what is I, Y, moment of inertia about Y, about Z, and about YZ is like a shear moment of inertia, centroid, shear center, other things, all mechanical properties that you may need for analysis. All right, but this is gonna be calculated and will be used by ANSYS internally. So you don't need to take note any of these, but I just wanted to show you how what this properties of this section are. So, okay, section 2 was what? Again, was circular and it was solid. The radius was what? It started from 1, and then after that we had 1.4, right? So it's gonna be zero point 0.7, the um, radius for that one. And then number 3 was again circular, but we had, if you remember, let me go show you, 1.625. So okay, let me divide that by 2. All right, 1.625 divided by 2, so I'm getting 0.18125. Okay, so this was section number 3. Section number 4, okay, I have 2 inches my diameter, so I'm gonna put here again, don't forget to change it to circular, and I'm gonna have it 1, right? Apply. Section 5 was again 1.625, so I'm gonna put that again circular, and I'm gonna change the radius to what I had, let me see, 0.8125. 8125, okay. So apply, and then you have number 6, again circular, was radius this time 0.7, right? So let me go back. Yeah, number 6 is gonna be 0.7, right? So apply, and then number 7, the last one, is point, again change it to circular, and then we have 0.5 for that, right? The last one, and I okay that. So we have our sections defined. We are gonna use that later. Okay, so next is the modeling of the shaft. So I'm gonna, as I said, I'm gonna model the shaft using actually like a single line, like a linear wireframe. So okay, so we are gonna generate some key points, and the key points, I'm gonna generate them as follows. The points that are important for us. I'm gonna define one key point here, so let me use my pen. Alright, so point 1, key point for my modeling. So this is point 1. Next point, this point is like midpoint of the bearing, right? This is important for my model, for my mechanical model. Alright, and then just hold on. Okay, so then I'm gonna consider a point here where I have the first shoulder, right? And let me write this down here. So point 1 is, I'm gonna call it like so point 1 and location, if I say X. position. I'm gonna start it actually from the center of the bearing as my point 0. So right, x is 0, then point 2 is gonna be where the shoulder ends, the for the bearing. So what is x for that? So let's see. If I call this 0, then that is one is 0.5. And then point 3, another key point, is where you have this shoulder starts here at this point. So what is the location position on that? Is 1.75, but it's going to be actually 1 because this is my reference right now. I'm considering the center of my bearing as my reference point, the center of that. Okay, so then point 4, you have what? I Next point is it's gonna be interesting for me is this point, the center of my gear, because I'm gonna need to meet requirements for the slope and deflection at that point, right? So my length, my position 2.75, but again I have to subtract that to 0.75, so it's like 2. And then next point, important point for my model, is this shoulder here, right? So where that starts, 3.7. So actually, yeah, so how much is like 0.75 added to this? So it would be 2.75 inches. Alright, so zero point 0.6, I'm interested in midpoint of the shaft to see how much slope is there, right? I want to see what it's like, how much slope and deflection I get there. So what is that point? We have to figure that out ourselves. So it's like 3.7 here, 7.5 here, so it's like 4. So I have to add 2 to whatever I had here. It's going to give me 4.75 inches for 0.6, and then 0.7. Another important point is this point, and it's gonna be how much I add to this, guys? 2, right? So because this entire thing was 4, so add 2, it's gonna be 6.75. Alright, so let's see. Next point, which is important for me, is 0.8. Again, the center of this gear, and I'm adding 1 inch to what I had here, 7.75, right? And 0.8 is okay. So 0.8. Okay, so you see the gear ends here, and then I have, okay, this is like the groove for the retaining ring, this one. So I'm gonna ignore that feature. So the next change that I have is happening here, and I'm gonna call it like 0.9 here, right? So 0.9 is what? Is 9.75. I subtract 0.75 from it. I'm gonna get this. So 0.9 is at 0.9, and then I have this feature here, 0.10, when they have the last shoulder for my bearing. 0.10, what is position? Coordinate x coordinate, 1025 minus 0.7, so it's going to be 9.5, right? And then last point I have is 11, the center of my bearing, right? So that length is 10.75, subtract 0.75 from it, so I'm gonna get 10. So this is what we had, and you remember when we did mechanical analysis, we had our entire length of the shaft, we considered 10 inches. That's actually mechanical length for what we needed for analysis. I'm gonna have that again, same thing for my, for my deflection analysis. So, okay, so we have everything, and uh, we know what type of section we have to use. Let's summarize that here. So for section 1s from 0 to 0.5 we have section 1, and from section point 2 up to point 2 you have section 1, right? After 2, so probably I have to have it like this. Between point 1 and point 2 I have section 1, and then between 2 and 3 I have what? Section 2. Between 3 and 4, point 3 and 4, I have what? I have section 3 and 4, section 3, and then D3, in other words. And then after that, between 4 and 5 I still have 3. So I'm gonna need these later when for modeling. So, and between 5 and 6 what I have D4, so I have to section 4. Between 6 and 7 I have section 4, still section 4. So, and then between 7 and 8 I have 5, and then between 8 and 9 I have still 5, and then between 9 and 10 I have D6, so 6, and then between 10 and 11 I have my last element, right, which is like my last section, 7. Alright, so we are gonna need this, so let me see if we can, yeah, okay, so I wish I had it like cleaner, but this is what we have. So let me see how can I zoom out a little bit, if I can. Yeah, but I think it's okay. Alright, so now I'm gonna define my points, my hard points or key points, based on those geometry, based on those x coordinates you saw. So point 1 is at say create key points, and then in axis coordinate system my point 1 is at point 0, right? So 0 0 0. Alright, so and then I say apply. I have my point 1 generated. Point 2, look at the x, is 0.5, so is 0.5, apply. Point 3, I'm sorry, 3 is position is 0.3, position is 1, and 0.4 position is 2, 0.5 position is 2.75, 0.6 is 4.75. It's the end of the mid segment of the shaft. So alright, so 0.6, let me see it again, 4.75, 0.7 is 6.75, 6.75. 0.8 is 7.75. 7.75, and 0.9 is 9. 0.9 is at position 9. 0.10 is 9.5. Okay, 9.5. And the last point is at point 10, right? The position is 10, which is the midpoint of my other bearing. Alright, so we have all our key points generated. These are important points that I'm gonna need. I'm curious about, deflections there. Actually, not all of them. What is important, you point one, which is where your bearing is located, midpoint of it, the gear, midpoint of gear, midpoint of the gear, and midpoint of the bearing. So these are critical points for me, but for modeling I needed the other key points. Okay, so we have these key points generated. Next, I'm gonna generate lines. So this shaft is gonna be modeled using a straight line. So I select point 1, point 2, so different pieces. Okay, different lines from point 4 to point 5, point 5 to point 6. The reason is each piece of this shaft we have different section, right? So that's why I'm defining new points everywhere, new lines, I'm sorry. So we have the line. So this represents my shaft and those critical points and